Welcome to the inaugural episode of our special series, When Rubber Meets, on My Rubber Heart. Today, we embark on a journey through a pivotal chapter in space exploration, marked by both innovation and tragedy. We delve into the Space Shuttle Challenger disaster, a moment that profoundly reshaped our understanding of material science and engineering. In this episode, we'll uncover the critical role of a seemingly minor component made of rubber and its significant impact on this historic event. Mission 51L, marking the Challenger's 10th awe-inspiring venture into space, was poised for a historic launch on January 28, 1986. This mission had a momentous objective: to deploy the second tracking and data relay satellite, the TDRSP, a crucial step in enhancing NASA's communication capabilities in space. But the mission was also unique for its diverse and talented crew, each member bringing their own story to this journey. Leading the mission was Commander Francis R.D. Scobie, a seasoned pilot and astronaut with a passion for flying that started in his early years. Joining him was pilot Michael J. Smith, a naval aviator and dedicated family man, who brought his extensive experience in test flying to this mission. The mission specialists comprised of Dr. Ronald McNair, an accomplished physicist known for his groundbreaking work in laser technology, and Ellison Onizuka, the first Asian American astronaut who had previously flown on the Discovery. Dr. Judy Resnick, another mission specialist, was a talented electrical engineer who had already made her mark as the second American woman in space. Gregory Jarvis, an engineer and payload specialist, was on board to conduct experiments on fluid dynamics in space. His inclusion in this mission was a testament to his experience and dedication to space exploration. Perhaps the most publicized crew member was Krista McAuliffe, a high school social studies teacher chosen for the Teacher in Space project. Krista's presence on the Challenger was a symbol of NASA's commitment to inspiring the next generation. Her plan to teach lessons from space captivated the nation and made the Challenger mission especially significant to both students and educators everywhere. Together, these 7 individuals formed a crew symbolic of expertise, diversity, and the pursuit of knowledge. Their mission was not only a technical endeavor, but also a journey of human spirit and curiosity. On the crisp morning of January 28, 1986, a frosty chill enveloped Kennedy Space Center. Temperatures had plummeted to an unusually low for Florida, hovering near freezing point. This unexpected cold snap brought with it a wave of concern among some of the engineers involved in the mission. On the eve of the Challenger launch, a crucial teleconference was convened. The focus: the impact of the predicted record low temperatures on the launch. The forecast was chilling. Temperatures as low as 18 Fahrenheit, which is -8 Celsius, overnight rising to only 26 Fahrenheit, which is -3 Celsius at lunchtime. Morton Thiokol engineers, responsible for the solid rocket boosters, voiced deep concerns. Their worries centered around the rubber O-rings, designed to expand and seal the rocket boosters. In these frigid conditions, they feared the O-rings' elasticity would be drastically reduced. The engineers highlighted past O-ring erosion issues in warmer launches and argued that they lacked the data for sealing effectiveness at temperatures below 53 Fahrenheit, which is 12 Celsius, which was the previous coldest launch. Morton Thiokol's vice presidents, Robert Lunt and Joe Kilminster, initially recommended delaying the launch until temperatures rose above 53 Fahrenheit. However, following a recess in the teleconference and internal discussions, Morton Thiokol leadership reversed their stance. They concluded the evidence on O-rings failure was inconclusive and assured a margin of safety despite potential risks. NASA, represented by SRB project manager Lawrence Molloy and mission management team leader Arnold Aldrich, was under pressure to adhere to the launch schedule. In their discussions, the specific concerns about the O-rings were not fully convened. The decision to proceed was made, despite Rockwell International's engineers expressing additional worries about ice forming on the orbiter, which could potentially damage its thermal protection system. The launch was delayed an extra hour to allow ice to melt, and after an inspection indicating the ice was melting, the Challenger was cleared for an 11:38 a.m. launch, with air temperatures at mere 36 Fahrenheit. This decision, against the backdrop of unheeded engineering apprehensions, set the stage for a devastating chapter in space exploration history. The underestimated risk of the rubber O-rings, typically an afterthought in rocket engineering, were about to manifest in the most tragic way.
This is shuttle launch control at T-minus 2 hours, 28 minutes and counting. Here comes the 51L flight crew boarding the elevator for the second time in 2 days, ready to depart the OAC building for the launch pad. They'll ride down the 3 floors to the main level, where they will exit the ONC building, traditionally met by the members of the media who are standing by, waiting to document. And this is the work crew here that has been very active in preparing the 51L mission, the operations and checkout building, payloads, which include a Tedra's satellite, Spartan Halley experiment. And here comes the flight crew now. Commander Dick Scovey, followed by Mission Specialist Ron McNair, Pilot Mike Smith, followed by Christopher McFarland, teacher in space, Ellison Amazuka, and Payload Specialist Greg Jarvis. Big smiles today. Confidently getting into the van. Everybody go up to that pad and attempt a second try. Second try at launch today. It'll take a few minutes for the astronaut van to get to the pad.
T-minus 15 seconds. T-minus 10, 9, 8, 7, 6. We have main engine start. 4, 3, 2, 1, and liftoff. Liftoff of the 25th Space Shuttle mission, and it has cleared the tower. Love you, though. Okay, out. So, Challenger.
Roll program confirmed. Challenger now heading down range. Engines beginning throttling down now at 94%. Throttle throttled for most of the flight, 104%. We'll throttle down to 65% shortly. Engines are 65%. 3 engines running normally. 3 good fuel cells. 3 good APUs. Velocity 2,257 feet per second. Altitude 4.3 nautical miles. Downrange distance 3 nautical miles. Engines throttling up. 3 engines now at 104%.
Challenger, go withdrawal.
Minute 15 seconds. Velocity 2,900 feet per second. Altitude 9 nautical miles. Downrange distance 7 nautical miles.
Ladies and gentlemen, I'd planned to speak to you tonight to report on the State of the Union. But the events of earlier today have led me to change those plans. Today is a day for mourning and remembering. Nancy and I are pained to the core by the tragedy of the Shuttle Challenger. We know we share this pain with all of the people of our country. This is truly a national loss.
At the heart of our story are the O-rings, which are small yet critical components of the solid rocket boosters. The primary function of these O-rings was to seal the joints between the segments of the rocket boosters. They were designed to expand upon ignition, filling any gaps and preventing the escape of hot gases. In essence, they were the guardians against the high pressure and high temperature environment inside the boosters. These O-rings were crafted from a unique type of rubber known as fluorosilicone, chosen for its remarkable properties. Fluorosilicone rubber is known for its excellent resistance to extreme temperature, fuel, and chemicals, making it an ideal choice for aerospace applications where reliability is paramount. But the utility of fluorosilicone rubber extends far beyond the realms of space exploration. Due to its exceptional qualities, it finds widespread use in various demanding environments. In the automotive industry, it is used for fuel hoses, seals, and gaskets, as it can withstand the corrosive nature of petroleum products and extreme under-the-hood temperatures. Similarly, in the manufacturing of aircraft, fluorosilicone is used in fuel lines, seals, and diaphragms, ensuring safety and efficiency under high-pressure conditions and exposure to aviation fuels. However, on that icy January morning, the properties of the fluorosilicone rubber were altered by the frigid temperatures. Rubber, at its core, is a material whose characteristics are heavily influenced by temperature. Under normal conditions, the O-ring's flexibility and resilience allow them to expand and create an effective seal. But the investigation into the disaster, as detailed in the Rogers Commission report, uncovered the fatal flaw. The cold temperatures drastically reduced the O-ring's elasticity. Their ability to flex and return to shape was impeded. This meant that when the boosters ignited, the O-rings couldn't expand as required to fill the gaps. Additionally, the hardness of the rubber, crucial factor in maintaining a seal, was compromised. Instead of forming a tight barrier, the O-rings remained rigid, leaving gaps through which hot gases could and did escape. This graph, extracted from the meticulous investigation of the Rogers Commission report, vividly illustrates how the cold impacted the O-ring's performance. It paints a stark picture of the O-ring's vulnerability. As temperatures plummeted on that fateful day, the crucial ability of the O-rings to maintain contact and form a seal was significantly diminished. But this wasn't an isolated concern. It was a repeated alarm bell that had rung before. Now, let's turn back the pages to previous shuttle missions, like the STS-51B. During these flights, engineers observed similar issues with the O-rings. Post-flight analysis revealed evidence of thermal distress and reduced sealing capability in colder conditions. However, these warnings were not fully acted upon. It was a pattern of oversight that would have dire consequences. In-depth testing of the O-rings conducted prior to the Challenger mission demonstrated their crucial dependency on two factors: ambient temperature and the initial compressive force known as the initial squeeze. Now, under ideal conditions, the O-rings would expand, filling any gaps and creating a robust seal. But the tests painted a different picture of the colder scenarios. When subjected to low temperatures, similar to those on the morning of January 28, the O-rings lost their elasticity significantly. This meant they could not expand effectively to seal the joints between the rocket booster segments. Moreover, the initial squeeze, the compression they were designed to exert, was insufficient in the cold. They were less able to adapt to the contours of the surfaces they were meant to seal, increasing the likelihood of a gas leak. Let's take a closer look at the engineering behind these O-rings. Each O-ring measured 0.28 inches in diameter, a seemingly modest size for such a crucial task. They were strategically placed within the field joints of the solid rocket motor during assembly. These joints are critical junctures where the rocket booster segments connect. The O-ring's primary role was to form a tight seal in these joints, preventing the escape of hot gases during the rocket's ascent. On the launch pad, as the Challenger awaited its journey, these critical factors converged. The cold temperature, coupled with compromised sealing capability of the O-rings, set the stage for one of the most tragic moments in space exploration. It was a stark reminder that in the high-stakes realm of space travel, every component, no matter how small, plays a crucial role. 73 seconds into its flight, a catastrophic failure occurred. The Space Shuttle Challenger was suddenly engulfed in a massive fiery explosion. The disaster unfolded in a harrowing sequence of events, witnessed by a nation in shock. The O-ring, compromised by the unusually cold weather at the time of launch, failed to properly seal. This failure allowed pressurized burning gas from within the solid rocket motor to reach the outside and impinge upon the adjacent SRB attachment hardware, an external fuel tank. The shuttle broke apart, its components violently tearing away from each other. The crew cabin, containing all 7 astronauts, was initially intact, but subjected to severe aerodynamic forces as it arched back towards the Earth. Tragically, all 7 crew members perished. The cabin was later found on the ocean floor, indicating that the crew may have survived the initial explosion, but were likely incapacitated or killed upon the violent impact with the ocean. This disaster marked one of the darkest moments in space exploration history, leading to an extensive investigation and the 32-month hiatus on the Space Shuttle program. The Challenger disaster serves as a profound lesson in material science. It highlights the importance of considering environmental factors in the design and selection of materials. In the case of the Challenger, the O-rings, made from a specific type of rubber, were not designed to withstand the unusually cold temperatures. This oversight in material compatibility under varying environmental conditions was a crucial factor in the failure. As we commemorate the Challenger, we are reminded of the relentless challenges and inherent risks of space exploration. This tragedy serves as a critical learning point in the field of aerospace engineering. It underscores the monumental importance of materials like rubber in the complex matrix of space design. In the wake of the Challenger disaster, the aerospace industry saw significant advancements in material science, particularly in understanding how materials behave under extreme conditions. These advancements have been instrumental in enhancing safety and efficacy of subsequent space missions. Thank you for joining us on this solemn journey through one of the most poignant chapters in space exploration history. It's a stark reminder that in the realm of engineering and science, the smallest components can hold immense significance. The tragedy of Challenger is not just a story of a failed launch. It's a lesson in how the intricate properties of materials like rubber can be the difference between success and catastrophe. Stay elastic, stay curious, and I'll see you in the next episode, where we continue to explore remarkable intersections of rubber with pivotal moments in history. Like, share, and subscribe for more rubbery interactions.